Now come to the surface defects. Surface defects means two-dimensional. I mean, till now we have discussed the point defect means zero-dimensional. Then the line defect means one-dimensional. Now we are moving forward to the surface defect means two-dimensional. Okay. So what is the surface defect? Defects are two-dimensional imperfection in a crystal structure that occurs at or near to the material surface. Okay, these defects arise due to the termination of a regular lattice at a surface or interfaces and significantly affect the material's physical, mechanical, and chemical properties. Okay, so what I mean, there are many kinds of the grains in a material. This is the different grains, this is the different grains, this is the different grains, and this is the boundary of the grain size. Okay, so this is the boundary. So different kind of the grains have grown in that particular crystal. Okay, so this is the different, this is different, this is different. Now, what are the surface defects? Surface defect means at the boundary, this boundary. If you see at the boundary, then boundary phenomena. Basically, the surface defect is a boundary phenomena. Okay. Okay. Termination of regular lattice at a surface or interface significantly means here the terminate. I mean, this grain has terminated at this particular boundary. Okay, and this particular boundary. From here, the different lattice, the different grain have been grown. So this termination, this the transition is known as your surface defect. Because surface, what we require? We require the overall the similarity. Okay, regularity. Okay, but here you can see there is no regularity. Here, I mean, in this region, some different grains have been grown. In this region, the different grain have been grown, and in this there is a different. So I mean, the termination means this way. I mean, this grain have their boundary here. I mean, at this boundary they have stopped growing, and since this boundary, different kind of grain have been grown. We talk about this way, then till here, that above this grain has grown, and after that they have stopped. They have stopped at that particular boundary, and after that boundary there's different kind of grains have been grown. Similar to that, we talk about the first top one. They have the same way, they have grown till here. Okay, and after that the different kind of the grain has grown. So this different kind of grain have emerged together, and obvious, if the different kind of the grains has emerged has induced, then there must be some kind of the boundary. Okay, so that is known as, I mean, that boundary behaves like the termination of one grain to the another grain. Okay, so this is the, suppose this is the A type, then this is the B type. Okay, then this is the C type. So A, B, C, and the three, I mean, in this example, particular example, three kind of the grain has grown over here, right? So this is a, this is your defect, because what we want the same kind of the grain must be followed throughout the materials. Okay, and if that has not been followed, it means there is a defect, and that defect is defined by the boundary conditions. Okay, so what where the boundary is present, that boundary will define till that boundary different kind of the grains has there, and after that the different grains has there. So this is the grain boundary. Okay, so if we talk about, I mean, the surface defect, the first one is the grain boundary defects. Okay, so this is the grain boundary defects. So occurs in a polycrystalline materials where the different materials, different crystals, different grains meet. Okay, atoms at the boundary are not perfectly aligned. Okay, as you can see. Yeah, you can see here around this particular line is, I mean, if you will follow the same pattern is here, same pattern, same pattern, same pattern. You see, same pattern, same pattern, same pattern. You can see here, same pattern, same pattern, same pattern. But at the boundary, you can see there is a vacant. There is, I mean, there is. I mean, this is the boundary, and if boundary near to the boundary, if you will collect top and bottom all the atoms, then you can say there is no such kind of the fashion would be seen. So it is the kind of irregularities. Uh, I mean, across the any boundary, you will observe the same kind of misalignment. This misalignment is known as your defect, and that defect is counted as a surface defect. Okay, any boundary you can take. Suppose if you are concerned about this particular boundary, see here, is there any fashion? No, they all are in ir- irregular way, right? So there is no such a fashion has been followed as here, here, and here. It is followed. So at a boundary, you will see there's a irregularities. There is no such fashion, and that kind of the uh, defect is known as boundary gain boundary defects. Okay, so create the regions of the higher energy due to the atomic misalignment. Okay, so what happens at the boundary? There is higher energy, and I have already told you that higher energy at any places is not required, not desirable in itself. The material or the in nature, everything try to be in their minimum energy. The minimum energy is the stability, and everything try to tends toward the stability. Okay, so it will disturb your stability. If the grain boundary is there, it means there is this higher energy, and higher energy will disturb your stability. So and that stability will basically make your crystal defect. Okay, so reduce the material strength, but increase the ductility. Obvious, if something is not in their own place, okay, that will reduce your strength. But why at the same time ductility is being increased? Because due to the misalignment. Misalignment, if you will stretch the body, some molecules will keep in contact with others. It will some like this. So there is no perfect closeness. That's why it will not ductile. It will not loose due to the misalignment. There is no perfect you know bond is there basically. Okay, so that's why they have the bond, but they have the little loose bond. A loose bond will provide you the ductility. That's why it will be able to stretch. Okay, so that's the reason you can stretch the material if there is a grain boundary defects. Okay, so as you can see here, there's some atom one atom is here, atom is here. There's no such a perfect alignment. If a crystal is in a perfect fashion, there is a perfect bond in between them, and that is a perfect bond will provide you the perfect strength. Okay, and if the perfect strength is not there, it means you have a less bonded atoms are there, and less bonded atoms will provide you the ductility that they can lose up to certain length or certain load. I mean, it depends on the load, not its length. It's about the load. That load will provide you the length. Okay, so obviously this is the way that the grain boundary uh, defects provide us the less strength and high ductility. Okay.